So up to this point, as we've talked about the momentum and we talked about impulse, we have tended to talk about the momentum and change in momentum of a single object, or the impulse exerted on a single object. And so all we want to do is say, well, clearly there are systems that are more complicated than single objects. So how do we deal with momentum when we have a system of particles? And so what we're going to do is we're going to define the linear momentum for a system of particles to simply be the vector sum of the individual linear momenta for each of our individual particles. So if I've got particles A, B, C, however many we've got, that to get the linear momentum of my system, I just need to do the vector addition problem to add up all their individual linear momenta. Well, of course, as a vector addition problem, this means that basically I'm going to be setting up component equations. So again, I'll calculate out what the x components are for each of my particles' individual momenta and then add those together. I'll do exactly the same thing to set up a y equation, to calculate each of the y components of my particles and add those together. So the nice thing about calculating the linear momentum of a system of particles is, again, fundamentally it's just a vector addition problem. So as an example, let's say I've got 3 particles, and instead of using A, B, and C, I'll label them mass 1, mass 2, mass 3. And so here they happen to all be coming together like they're about to collide. Fine. Well, what I want to do if I want to figure out the total momentum of my system is basically, like with any vector problem, I'm going to pick a coordinate system. In this case, using our standard positive x pointing to the right, positive y pointing up seems as useful as any. And so now I can redraw the 3 momentum vectors that I care about here that I want to do my vector addition over. So I know that the velocity vector for mass 1 points down and to the left. It makes some angle theta with the negative x-axis. So the momentum of particle 1 has to point in that same direction. The velocity of particle 2 points in positive y. So the momentum for particle 2 also has to point in that direction. The velocity of particle 3 points in positive x. So again, the momentum of particle 3 has to point in positive x. And so all we're going to do is say, fine, there are the 3 vectors that I need to add. Well, I know how to break vectors up into their components to do the addition. So again, I'll have an x and y component for the momentum of my system, and that's just going to be adding together the x components in one equation and the y components in another of each of the individual particles. And so I can take those 3 vectors that I've been given in my example here and break them up. So I know that for particle 1, its momentum is going to have a negative x component, negative y component. The magnitude of both of those is going to be p1. Given what that angle theta is, it's going to be cosine angle theta for the x component, sine of the angle theta for the y. P2 points in positive y, so x component 0, and all the magnitudes in the y component. P3 points in positive x, so y component 0, and all the magnitude points in positive x. I can take my table, set up my 2 component equations. So again, I'm just adding together the x components of the individual momenta to get the x component for my system, doing the same with y. And so when I set those equations up, again, I can now come back and say, well, the magnitude, if the information I was given was in terms of mass and velocities, I can plug in that the magnitude for the momentum of particle 1 is m1v1, the momentum of particle 2 is m2v2, and the momentum of particle 3 is m3v3. So this gives me the way to calculate out what the x and y components of the total momentum of my system are. And so this is basically just giving me the vector sum of those 3 momentum vectors. Again, if I've got x and y components, if I need to, I can Pythagorize those to get the magnitude of the linear momentum of my system. So x component squared plus y component squared, take the square root. Or I can take the inverse tangent of, again, if we choose to do y component over x component, then I'll get an angle that's relative to the x-axis.